Okay, we're finally ready to talk about rotations in 3D, one of my favorite topics. So first, let's remember how we did rotations in 2D. So our goal was to move things around, but to not stretch them or shear them or flip them in any way. And another way of saying that is if we think of starting off with the x-axis pointed some way and the y-axis perpendicular to that, we want them to move and remain perpendicular as they're moving. So that's our goal. So they should keep right angles to each other. And if we do that, what we see is that the x-axis turns into the vector cosine of theta sine theta, and the y-axis unit vector turns into the vector negative sine theta cosine of theta. And we remember from our column interpretation of a matrix multiplication that we can then just put that where the x vector went into the first column and where the y vector went into the second column. So we're going to do something very similar in 3D. We could actually maintain three vectors and keep them perpendicular to each other. So we'll see where the x-axis goes, we'll see where the y-axis goes, and where the z-axis goes. Turns out it's actually a little bit simpler if we break it down into a few cases first. So let's consider the case where we're rotating counterclockwise around the z-axis. So the z-axis will remain fixed, but the x-axis and the y-axis will move in the xy plane. Now the z-axis remaining fixed is just saying, hey, the z direction was 0, 0, 1 before. It's still going to be 0, 0, 1. So I've already got my third column figured out there. But then my x-axis moves to the vector where I can see that its x component gets cosine of theta, and then it moves towards the y direction, and its y component gets sine of theta. But I didn't move at all towards the z direction. I stayed in the xy plane, so my z is 0. So I have cosine of theta, sine of theta, 0. Actually, I'm using alpha here, not theta. Okay. And then we see that, okay, well, when the y-axis rotates, the y part gets cosine. The x gets negative sine, because, see, we're moving away from x. We're actually moving to the left. And then, again, it stays in the xy plane, so the z is 0. So now we have our other vector, negative sine, cosine, 0. So that's all there is to it for the rotation around the z. And you notice that really, we were always doing that all along. When we were working on a flat sheet of paper, kind of in the background, there was a z coming out towards us. And so it's really the same equation. I just added a row and a column, and I'm saying put a 1 in the lower right so we keep z the same. So let's go to our trusty viewer and look at an example. So my favorite example is rotation by 45 degrees. Sine of theta and cosine of theta are both root 2 over 2, which is approximately 0.71. So if I follow this equation here, let me move this over so we can see them both. So if I follow this equation, then in that case I'll put 0.71, negative 0.71, 0.71, 0.71, and I'm good to go. So let's see what that looks like. Okay, so this is the z-axis. Actually, it's coming out towards me here. And so I'm rotating counterclockwise around that axis. And what I notice is, yes, that certainly looks like 45 degrees, and it also preserved all the right angles in the box. So that's good. We're trying to keep everything orthogonal. All right. So what other kinds of rotations can you do in 3D? Well, let's look at each of the axes in turn. Let me go back to the x-axis now, and let's say, okay, I want to consider a counterclockwise rotation about the x-axis. And that arrow shows what that direction would be. And here what we see is, okay, let's look at the z-axis. We see that z gets the cosine of theta, and y actually gets the negative sine of theta. See how it's moving in the xy plane, but it's actually turning away from where y is pointing. Okay, so we can set up the z column now. And there's nothing, neither the y nor the z move at all in x. So now x gets 0, y gets negative sine, z gets cosine. And then we see for the y-axis, well, the y gets cosine of the angle, and then a sine component moves into z. So here we have, and nothing goes into x. So x is 0, y is cosine, z is sine. And then x stays fixed. So the x column is 1, 0, 0. So this, these look pretty similar. It's just where do you put the 1? So here the z stays fixed, here the x stays fixed. So let me go and try that out now. So I have to change this. So now I have a 1, 0, 0 here. But now I'm going to put, okay, so the cosine 0.71, negative sine, sine, cosine. So let's look at that. Okay, so now we see we're rotating in that direction, exactly the direction I specified here. We're moving that direction around the x-axis, so the red axis there. So let's watch it again from over here. And we see there's a 45 again. So the box stays like a box. All the right angles are there. But now we're rotating sort of towards us, so counterclockwise around the x-axis. Okay, so there's only one more case we need to consider. And that is rotating about y. Now it's the same kind of thing, except we kind of break the pattern that we've seen a little bit so far, so it can be a little confusing. So I say this one hurts the brain a little bit. But we're just rotating counterclockwise around y, so here's the arrow that shows it. And so what I see is I move z over here, so z gets the cosine of this angle, and x, positive x, gets the sine. And then the x, if it's moving in that direction, well, we say x gets cosine, but then z gets negative sine, because see, it's going against the z there as it rotates. Stays in the xz plane, so y is going to get 0, 1, 0. And if I line these all up, I see that, okay, x is cosine, z is negative sine, and then of course y remains 0 for the x. And then the z, well, x gets sine, so there we go. Y remains 0, z gets cosine. So that's all there is to it. The only thing that gets confusing here is notice it kind of broke our pattern. We used to have cosine sine, negative sine cosine, but see this, it actually flips here. And that's just because we're trying to be consistent with our right-hand coordinate system. And this is one of the weird things that happens when we do that. Okay. But that's all right. Just follow this formula and you'll know which direction you're going. So this is counterclockwise around y. If you mess up the sign here and you flip this around, you'll just end up going clockwise instead. But we like counterclockwise angles because that's the convention we've decided to stick with. Okay, so let me start over here. I'll just go back to the identity for a second. Okay, and so let me see if I can do that counterclockwise rotation about y. Let's see what that looks like. Okay, so cosine, so 0.71. And here we have a sine, negative sine, cosine. There we go. Okay, so see that nice counterclockwise rotation in the xz plane. So with my y-axis as the axis of rotation. Okay. And of course you can do more than one rotation, one after the other. So let's say that I first wanted to do that rotation, so I'll do exactly the one I just had. Let's say after that I wanted to rotate around the x-axis, so keeping this row 1, or keeping this column 1, 0, 0. I wanted to rotate around the x-axis, we'll say by 90 degrees. Okay, so cosine of 90 is 0, negative sine of 90 is negative 1, sine of 90 is 1. Okay, so let's just check that. So there's our 90-degree rotation around the x-axis. You see that there. Here's again our 45-degree rotation about the y-axis. So let's see what they do one after the other. Okay, so 45 in y, and then we get that in x. Okay, so that's what that looks like. And if we do them all at once, that's where we end up. Okay, now the really fun thing is we can actually get to any possible rotation in 3 dimensions. I'm going to show you. You'll do an assignment like this. I have to fix it up. But last year, I gave them an assignment where they're exploring something called Euler angles. So you can actually think of rotations in 3D as you can decompose any rotation in 3D, it turns out, into a rotation around X, a rotation around Y, and then a rotation around Z. So, and you can also realize this with a system of what is known as gimbals. So here, what I do is I first rotate around. So if I'm sticking with the coordinate system I had before, this is rotating around the z-axis. And once I've rotated around the z-axis, I can then rotate around the x-axis. So that's called pitch. And then once I've rotated around those two, I can rotate around the y-axis. That's called yaw. And so I can make this plane point in any direction that I want by specifying these 3 angles. So we'll play around with this more later, but I just wanted to show you that. So it really does help us to break it down into a rotation around the x-axis, a rotation around the y-axis, and a rotation around the z-axis, because we can reach any rotation from any 3 of them. Now the order matters, as you'll see in the next exercise. But once you fix an order, then you can reach anything you want. Okay. And notice, no matter what we've done, we've kept these axes orthogonal. So what you'll see, even after you do, I could do kind of a crazy sequence of rotations. What you'll see is the matrix that gives rise to putting the plane in this direction will have 3 perpendicular columns. The columns will always remain mutually perpendicular. Okay, so now I want to have you play with rotations real quick, and then we will move on.